Okay, I also want to make an announcement. I will be traveling starting tomorrow. I'm going to be on a 6 hours time difference, but next week we're going to do a virtual class, unfortunately. It's reflected on the syllabus. So we're going to meet on the regular Zoom channel, but it's virtual for all of you. So I apologize for that. It's meant to be an in-person class, but yeah, I couldn't change my schedule, unfortunately. But I'll be back the week after. So on the 21st, I'm going to be back and we're going to do in person again. But it's just next week, it's going to be a Zoom session. Good. Okay. So today, just quickly outlining what the practice lab will look like. And this, okay, so today we're really going to look into more of the descriptive aspects of things. We're going to do a little bit more of graphical displays. And descriptive statistics, as we talked about, the main tasks of statistics, it's really descriptive statistics and it's inferential statistics in addition to the planning and design of analytic approaches as well as trials. So you always want a statistician on board when it comes to the planning of trials. So the descriptives are really a major part of it. Basically, when you look at the analysis of any study, the most important things are really the statistics. So this is really the heart. And based on the statistics, you will, just by the naked eye, either in graphs or in numerical form, in tabular form, you will find signals that essentially will inform then where the thought process needs to go when building models, when building regression models, or when building probabilistic models like logistic regression or Cox regression. So it's really descriptives, well presented, well analyzed, are really half the paper. It's really as important. So for that reason, we're going to dedicate the practice lab 2 today to an investigation of a data set. This is data from the behavioral risk factor surveillance system. So this is actually a really large telephone survey that was conducted in the US. So this is really valuable and really super important data. We have a random sample of this survey and we will just test it a bit, look at it. And this is data hypothetically that also is available if you're more interested in that rather than the enhance. Feel free to also use this data set, for example, for the final project. So we're investigating it, we're describing it, we're describing them continuous variables with the markers of central tendency and variability that we will be discussing today. And there are some exercises involved for you, how you can also subset data and repeat analysis in a subset only. And then we're also going to look into categorical variables and we start to summarize categorical variables in the form of a frequency table and then translate this in a bar plot. So these are simple exercises, I'm well aware, but you're going to have that code at your disposition. So not only will it be helpful for the final project, but you don't know down the road in your academic career or in your professional career what you will be going for and which direction you're gonna at one point develop, and maybe it's code that will be useful for you at one point. So these are really the basic codes that will help you down the road. Good. So if we open the PowerPoint presentation, this will be really where we're going to continue this today. So we are talking about frequency table, bar plots, histograms, box plots, dots plots. These are the numerical tabular formats, how to present data. These are the graphical ways to depict data. We're measuring the center with mean, median, and mode. We're measuring the spread. And this is really also quite important because it's the variability. It's the variability around which the distribution presents. So you have a central tendency, which is the center of your distribution, as the name implies, and then you have the variability that forms the shape of the distribution, essentially. And we talked about this briefly already in last class. So we're talking about standard deviation, variances, interquartile range, and ranges. Let's remember, we have these terms. We have a population that is a defined population that we're looking at. We have a sample that is a subset of this population that essentially represents a representative sample. And this will be, we will discuss this in more detail next week when we talk about sampling. because sampling is really of enormous importance, because you want a sample that really reflects your population. And that's actually not always the case. Bluntly spoken, it's in randomized controlled trial, for example, and you will have this lecture in the other class. Unfortunately, this is rarely the case. It's very hard to find a perfectly generalizable sample that really reflects that population you're interested in. There's, for example, work that basically suggests that pretty much all the trials that are conducted on blood pressure medication or all other medication are basically not representative of the Medicare population that will essentially then receive that medication. So that's actually a huge issue, right? That's why it's important to look at it also then in a post-market evaluation and see how that really then presents and performs in a real-world setting. So we talked about descriptive statistics, we talked about summarization and visualization, and then the inferential statistics, where we're basically learning about dynamics in the population based on the dynamics in our sample, which we look at under the assumption that the population dynamics will be consistent with those that we see in the sample, where external validity and generalizability of the sample to the population actually becomes of utmost importance. So a variable is a characteristic that is recorded for each of the subjects. We have, again, we have nominal variable that can be binary and are categorical in nature. If they're binary, you only have 0 and 1s. If they're categorical, you have more than 2 groups. Hypothetically, binary also is a special form of categorical variables. So this can be treatment groups, marital status, and races. This can be ordinal as soon as you have an order imposed on that variable. And then based on this, you can have quantitative terms. This can be continuous, like classically height, weight, and age. These are the typical variables, but can be all other variables, can be blood pressure, can be lipid levels, can be cholesterol, you name it. And then you have discrete, which is basically a reflection of counts. So if you have categories and you would categorize now couples that have no children, couples that have 1 child, couples that have 2 children, couples that have 3 or more children, the categorization, that would essentially be an ordinal variable. But the count for each of these categories, that would actually be a discrete variable. So the count would be discrete. So that's how these differ from each other. So just as a recap from last time. So nominal ordinal data summarization. So this is where we talk about frequency tables or contingency tables. So these are best displayed as a bar plot. So essentially you have here the example from last time where we talked about the severity of pain in patients that received the treatment or were in the control group. So basically you have 20, 30, 50, these are the counts. So this would be the ordinal variable, whereas this would be discrete variable. And this is then summarized in a frequency table or in a contingency table. Okay, we talked about some bar charts are to be preferred over pie charts. Yes. Yeah. So the problem is a pie chart shows the same information as a bar chart, but it doesn't show it effectively because essentially you don't see the numerical value, and it takes off a lot of space, but not providing additional information. So a bar chart is much more informative, and it also allows the direct comparison between the 2 bars, whereas the pie chart actually doesn't allow you to compare between those groups. That's the point that Professor Wharton wanted to make here. Okay, frequency, proportion, and percentages. So we did calculations already last time with data from Dr. Abusnad. So keep in mind that if you have a frequency, that's a count. If you have a proportion, that's basically that count divided by the number of all entries at your disposition. If you multiply this by 100, you get to a percentage, but we've done that last time. All of this can be shown as a frequency table as well, and can be also shown in a bar plot. We talked about dot plots, histograms, and box plots. Dot plots basically show a dot for each entry, whereas histograms categorize the data according to bins. And these bins will determine how granular your information is. So in the most smoothed, most granular format, you essentially create a function and you create a frequency polygon. We had this distinction last time, if you remember. So you basically can connect only the upper level of the bins with each other, and you basically get like just a connection between those upper levels, or you can actually fit a mathematical function through that, and you basically smooth it, and you have a smoothed frequency polygon. So, but all of these, in essence, will help you to identify central tendency, which basically demarks the center of your distribution. It will allow you to quantify the spread, which is basically the spread of your data around that center of your data. Then you also will see skewness. Skewness essentially indicates, and we will talk about in a second, it will show you in which direction the distribution shifts. So if you have outlier, your histogram will be pulled and will have very long tail to the right, for example, if you have positive outliers. So that's a right skewed or positively skewed distribution. If you have outliers that are pointing more to the negative end, so pointing to zero or even pointing negative, depending on the data that you have, you will talk about a left skew or a negative skew. And all of these also help you to identify outliers. And these outliers are extremely important because they're outliers for a reason. And excluding outliers, although damping, is not always a good idea. It's in most cases not a good idea because there's a reason why they're outliers, and you need to understand those outliers. So sometimes in analytic approaches, particularly when you look at regression models or probabilistic models, it's tempting to remove outliers. Don't do it. Don't do it if you don't have a proper justification for it. And that justification needs to be scientifically really sound. Because if a statistical reviewer catches you like excluding outliers, they're not going to look favorably at your work. So it's really outliers always need to be understood. They need to be investigated, and there needs to be a justification in case you opt to exclude them. So as said, dot plots show every individual observation. To be 100% perfect, I have never used one in real life. So it's rather, if you really have a very small sample, then you may consider using that. But in the end of the day, it's not a very it's for larger data sets, it's absolutely not useful. For smaller data set, it gives you a taste of the individual data points, but there are also alternatives to depict this data, which we'll discuss later on. So more common, and this is, if not even the most common way of depicting data, is a histogram. So in a histogram, we talked about it. So we did our first histograms now with Dr. Arbuthnot's data. The binning is really key. And the binning can either be done in an automatized fashion, or the binning can be done in arbitrary fashion with predefined bin categories. But what you really want to see is this distribution. So this data, for example, is not perfectly normally distributed. And many of the methods that you're using require a normal distribution. So if you have, for example, data that is absolutely not normally distributed, like this, you probably would get away to some shape or form because you have one peak, which is one mode, which we'll discuss later what that is. But you probably could use a quote unquote parametric test, which is a test that makes an assumption about your distribution and assumes it's following a normal distribution. The opposite of that is a non-parametric test, and the non-parametric test actually allows for you to analyze data without making assumptions about the distribution of the data. So the non-parametric test comes with a couple of caveats, and it's resulting in some misclassification. It has a higher probability of a type 1 error. So it's a little bit more problematic. So you would prefer a parametric test over a non-parametric test if the distribution allows for that. So Yes. We're getting there. So you would see a typical normal distribution is, well, good point. It would be good timing to now show a normal distribution. A normal distribution traditionally is the typical Gaussian bell curve. So basically you have a bell-shaped distribution. So this histogram would basically be perfectly symmetric. It would have the shape of a bell, indicating some outliers to the outside, but basically with the center, the bulk of the data being in the center with one mode. And the most important thing of this is that it is symmetric. That means you go mean, median, and mode, which we'll discuss later what that actually is. They're splitting this bell curve into half, and it's symmetric on both sides. And this becomes important when we talk about standardization, but more about that later. But yeah, good question. So it's bell-shaped, symmetric, and it's bell-shaped and symmetric, yeah. And with one center. So the effect of the bin size is here presented, and this is where the bin size is important, because you are increasing the granularity of the data that you're presenting. So if you're minimizing the bins, this is why the bins are so important, because if you minimize the bins and you make the bins smaller, that will result in you getting a more accurate reflection of what that distribution actually looks like. That's why the most accurate way of looking at this data is basically taking your data, fitting a mathematical function over that distribution, and showing it as a frequency polygon, because that shows you the density of the data points. So that function will be built on the density of the data points in reference to the entire data set. So sometimes you need to weigh detail against increasing summarization, and that depends mainly on the research question you're asking. So if you have an interest in particular bins, like for example, think of a body mass index. So body mass index, I guess all of you are comfortable and acquainted with this as a parameter. That would be the weight divided by the height in meters squared. And you have values that are starting for normal from 18.5 to 25. That's kind of considered normal as per the WHO classifications. Everything less than 18.5 would be considered underweight. Everything greater than 24.25 to 30 would be considered like a little overweight. Everything greater than 30 is overweight, obese, and everything greater than 35 is severely obese. So this being kept in mind, if you have a histogram showing you in exact granularity how the data distributes, that's important for your own information, because you know then how your data distributes. So it's important for various reasons. But in the end of the day, what you really want to do, you want to customize those bins to what actually is used by WHO criteria, and you want to know the frequency in these respective bins. So that's a use case where you would use customized, individualized bins rather than automatized granular bins. So again, the wider the bin, the more summarization. The smaller the bin, the more granular data you get, and the more likely you have an accurate reflection of your distribution. The interpretation of a histogram essentially is always following the same outline. So you look for a center, you look for a spread, and you look for a shape. So essentially the center is either the median, which is basically demarcating the half of this data. So this is the middle score. Greater than the median, that's 50%, smaller than the median, that's another 50%. Then you have the mean, that's the arithmetic mean, as opposed to, for example, the geometric mean. But the arithmetic mean basically is in a perfectly normal distribution, identical to the median, and it basically is exactly at that middle. And there you will also find the mode, which is basically the peak, the highest, the summit of your normal distribution. So basically where the bell is hanging. Then you have the spread, which we'll talk about it today, and then the shape. So this is the skewness that I briefly talked about. And the skewness is basically described as per the direction. So it's either to the left or the right side. It's either left skewed or right skewed. And what's the mnemonic? The tail tells the tail. So the tail basically shows you which direction. So if it's pointing to the right, it's a right skewed distribution. If it's pointing to the left, it's left skewed or negatively skewed. What's important is then, so you may have heard, some of you that have a little bit of a statistic background, you know about flooring and ceiling effect. A ceiling effect typically is where you have an upper threshold. So if I look at your quiz grades, when we take the quiz, that will have a ceiling effect because there's a natural boundary. So there's 100% and you can't have more than 100%. If there's a lower limit, you have more of a flooring effect. So if I have a really tough quiz with the flooring effect that everybody is like closer to zero, that is a flooring effect. If I do a really easy test, everybody is to the ceiling, to the higher end, that's a ceiling effect. You have, so if you want to determine variables that are more likely to show a right skewness or left skewness, you always have like examples in mind. So for example, lifespan is something that is typically always, so the bulk of the data is shifted to the right naturally, and the outliers are really more to the left end, so that is typically left skewed distribution. The income, household income or individual's income is something that is more likely to be right skewed because only the outliers will earn more than the median and more than 75% of the population. Modality, and now we're coming to the mode. So any questions to skewness? I think this is all super easy and quite intuitive. You certainly have heard it already in some shape or form in previous education. So then we have the mode. So the mode is basically characterized by the highest peak. So if you have one bar that is the highest, and that clearly is the center, and that's the highest point, that's a unimodal distribution. If you have two comparable modes or peaks, then you would speak about the bimodal distribution, or you can speak of a multimodal distribution. And there are various reasons why you would see these distributions. Example is, for example, if you have a time series and you calculate the frequency, what is the example I show my undergrads? It's like the frequency of the name Violet. That's actually, and there was a super popular name somewhere in the beginning of the 20th century, then totally disappeared. Nobody named their children Violet, and now it has an advent again, and now we're basically back at the peak of the violets being born each year. So it's kind of interesting. So there are various other examples I could think of. Inflammatory markers. So when it comes to life sciences, inflammatory markers, for example. So bulk of individuals will CRP, C-reactive protein, acute phase protein produced in the liver, basically acts against acute inflammation and acute infection, so to say, will increase quite rapidly. The liver is producing this quite abundantly to fight that pathogen off. So healthy individuals will have a low CRP, usually less than 10. If you have an ongoing infection, this will increase rapidly, but then kind of like level off, and then you have a second mode, bimodal distribution in many cases, in some populations, right? It also depends on the research question asked, but that's an example where you could see that. So CRP is a classical example, which is virtually, I've never seen it normally distributed. So, okay. Any questions on modes? I think it's quite simple. Good. Outliers. Outliers falls far from the rest of the data. They really need to be looked at. And they're actually super interesting to look at. Because in life science data that is really coming with a physiological or pathophysiological relevance, these outliers are outliers for a reason, and the reasons for that are basically, in many cases, of the separate research paper. So it's really important to pay attention to them and really investigate them. Do not remove them only with a proper justification. And that's also true for the final project. So if you have outliers that you don't like and your model doesn't fit well, it's like, don't just remove them. I'll find them. So, yeah. Okay, box plots. We talked about box plots. So that's just a really nice way to depict data. You essentially, we talked about this stratification. So you basically have in the box here 50% of the data. So you have your Q1, that's 25% of data is to the left of Q1, 25% of the upper level of the data is to the right. Here are the 50%, that's the middle score. And here we have, this is the IQR, that's the interquartile range. And you have the whiskers are basically Q3 or Q2 minus 1.5 IQR or Q3 plus 1.5 IQR. It's important to keep that in mind because this is your identification of outliers. And that's these you can identify. And once you know these outliers, you see them in a box plot, and then you have that group of outliers that you really want to look at. There's a modification of a box plot, which is called a violin plot. So the violin plot, that's actually, it's a pretty graph where let's try to dig out that code. So basically a violin plot is a box plot embedded in a histogram, in a frequency polygon. So it's basically, it's surrounding the box plot in the shape of the distribution. So you're basically merging the distribution, the frequency polygon together with the box plot. It's a aesthetically very, very nice graph, and it's quite insightful. Can be a little busy if you have a few of them, but yeah, it's a very nice graph. I'll find you the code. The beauty of a box plot is really that you can compare distribution. You cannot make inferences, so you could not say this one is significantly different from this one because these are medians, which are kind of stable against outliers. But you can kind of assume that there are differences between these two cohorts. So, so you could compare here the differences between biological sexes. So you have males versus females, and you could, based on that box plot, you can say there is likely some form of a difference, but it would need to be formally tested whether this is significantly different. Good. So now we're getting to the actual summaries, and I will move fast because all of this, you know, all of this. This is, so you know, just for the notations, I think that's important. You have here an X bar. When you look into population parameters, and I emphasize parameters because the mean in a population is called a parameter, whereas in a sample, it's a statistic. That's an important distinction. And the parameter in a population is labeled with a Greek letter. That means that the mean in a population is basically called mu. And that's like, yeah, the Greek letter mu. We'll get to that later, but in a sample, it's a statistic and it's X bar. Well, there are variations. It can be M, it can be mean, X bar. X bar is most commonly seen whenever you look at that. As for the mathematical notations here, you have 1 over n. So n always stands for the sample size. So that is, if you have a random sample of 20,000 subjects of that survey, of the BRFSS survey, n stands for the sample size in your sample, so that's 20,000. This is the Greek epsilon, that stands for sum. You see on top of n, you always see the end of your iteration, so to say, of that sum. And at the bottom, you have the beginning. So I equals 1 indicates here from the first subject to n, which is subject 20,000. So it's basically the sum of all subjects. So you're summing up all subjects from 1 to 20,000. And each individual I, so I will iterate from 1 to 20,000, 1, 2, 3, 4, until 20,000. And each individual iteration of that X will basically be summed. So all of this is summed. So that's a mathematical notation. Why is this important? Because we will build iterative loops in R, which basically repeat the same process over and over and over and over and over. And this is why I is just a typical classical counter. For each iteration, you count it up from 1 to 20,000. Okay, the mean is not resistant. So the problem is the way the mean is calculated, you change one number in your mean, there needs to be a change in your estimated mean. So you change the serum cholesterol of subject 19,998, your mean will need to be different because it's arithmetically summed up and then divided by the number of entries. So that's why it always needs to change, which makes it very susceptible to change due to outliers. And this already emphasizes the difference and the advantage of a median over the mean. I'm not saying it's always preferable, but in many cases, particularly with outliers, always go for the median if you have outliers. And so now here you have 4 different distributions. You have normal, log normal, exponential, and uniform distribution. And you basically see 2 things. You see that the normal distribution, the mean and the median are almost identical. In a uniform distribution, it's almost identical. As soon as you have an exponential, which is an increase like this with either a left skew or a right skew, depending on which direction the exponential function points, you see skewness, and this is important. And this is an important quiz question. I'm flagging that too. If you think about it, so the mean is the middle score, right? I will talk about this in a second. Oh yeah. So here we have 7 dwarfs, right? So the median is resistance against outliers, but if you replace the 7 dwarfs with a couple of basketball players where one is particularly large, will the median change? So these are not my graphics, Professor Waldron. He has a sense of humor, I don't. So basically, the median will not change, even if you have outliers in your data set. So if you were, okay, let's assume this individual is the same height as the other players. The mean and the median would be at the same spot. So now suddenly that player steps out and number 21 comes in and he's a little taller. In which direction will the mean change? Exactly. It changes in the direction of the outlier arithmetically because it adds to the sum, then you divide it, but you still divide it by the same number of individuals, right? So it needs to be a change in the direction. So if I show you now, okay, those are the 7 dwarfs. Okay. And you see this here, right? You see this here to some extent by seeing this mean pulled towards the outliers. So this will always be the case. It's pulling the mean in the direction of the outlier. So which one changes the last? You add a bunch of outliers to your distribution. So you have now 3 markers of central tendency, mean, median, mode. If you add a bunch of outliers that are all positive, greater than the mean changes always. Which one changes the last? Yeah. No, the mode. Because the mode is the highest peak, right? And the highest peak is not changing. It's like even if you have a little bump on the right, it's not automatically a bimodal distribution. So it's really the last that changes. Okay, the median is also the 50th percentile. I'm not going to walk you through the calculation. Although even that doesn't, it's a subtlety if you do it by hand, but I don't think that's relevant. In the end of the day, you use the median function R to calculate the median, or in Excel. Okay, the median is here the same. We talked about this mode. the value that occurs most often changes with the width of bins. Skewness, we talked about skewness. This is exactly what I talked about before, 90th percentile. That is important when we talk about, okay, so the percentile, if you have a distribution and you quantify percentiles, a percentile as per definition is basically characterizing what percent of your sample population is below a certain number. So each of these, okay, so we have the histogram, that's the frequency, that's the actual marker, be it body mass index, blood pressure, whatsoever. So you have each of these entries here will demark one value, one possible value for the continuous variable. If you have one marker here that characterizes a certain percentile, that means it quantifies whatever is less than this value. So the percentile characterizes which proportion or which percentage of your sample population or population is below a certain threshold. So when we have interquartile range, we have 25th percentile and 75th percentile. As per definition, Q1 demarcates that point where 25% of your population are below that certain value. Same with Q2, which is consistent with the median, that's another 25%. So if you want to know 25% in between 25th and 50th percentile, that can be calculated with Q1 and Q2. And we will do that calculation today. It can be simply done in R. Same with 50th to 75th and 75th to 100th percentile. Where 100th percentile is basically the maximal entry. So that max of your data set. Whereas the minimal entry is 0th percentile. That also then basically range demarcates 0 and 100th percentile. So range is max minus min. I personally, so you can report ranges and IQRs as an actual difference. So you can calculate the difference between max minus min. That's the actual range. I favor in terms of reporting that you would use the minimal entry and the maximal entry rather than just calculating the difference, because it's easier to look at an interval than just knowing a numeric value, which constitutes the difference. That's not super informative in a way, right? Okay, this is, yeah, now we're getting a little bit more complicated. So now we're actually looking at any questions about central tendency. I think that's super simple, right? Okay, so now we're getting a little bit more specific. Now we're getting into the discussion of the spread. So that's the variability. Okay, so we have the bell-shaped curve. We have this normal distribution. Now we want to know, how does that data actually distribute around that center? And so there are two things that you certainly have heard, and that's variance and standard deviation. And I want to just quickly walk through the arithmetics of this. We're not going to do the calculations. We're not going to go that deep. But I think conceptually it's important to understand in principle what that is. What you're doing, so that's the core piece, is this. The core piece is the calculation of each, and we have again this notation, so from 1 to 20,000. So we're doing this again, we're doing this 20,000 times. We have x1, x2, x3, x4, and we are subtracting from our individual entry the mean. So we're getting a deviation. That deviation, since it's on both sides of the mean, because it's the spread around the mean, and the mean is in the center, it can be positive or negative. So that is a deviation from the mean. When you square this, you get a squared deviation. Then you get 20,000 squared deviations, logically, right? Once you square a negative number, that negative number gets positive. So this becomes a squared deviation that is always positive. Now you're summing that up and you get a value that is extremely important and will become very important when it comes to regression analysis. You have a sum of squares. If you sum all of these squared deviations up, That's the sum of squares. The sum of squares is for both ANOVA and regression a super important marker for variability. So this sum of squares, so that's the formula for sum of squares. You're dividing this by the sample size, or more specifically here, the sample size minus 1, because it's for a sample. We're not getting into the depths of that. That will be confusing at this point, but you're dividing it by your sample size or the degrees of freedom, n minus 1. And what you do, you get an average squared deviation. That's what the variance is. It's an average squared deviation. So you have 20,000 squared deviations, you divide them by the number of entries, you get an average. So it's an average squared deviation. That's the variance. That's an average variance in a squared format. If you are now square rooting this squared difference, that's actually the wrong formula. That's a terrible formula. Squared deviations. Yeah, that's squared deviations. If you are square rooting, okay, I don't like this formula. Okay, so that's the standard deviation. So that would be xi. Okay, if you have each individual, so this is again the sum of squares divided by the sample size, or degrees of freedom in this case here, and you square root this, you get the squared deviations, you get the average squared deviations. You're square rooting it, you get to the actual deviation irrespective of the sign, and that becomes your standard deviation. Make sense? So you take that square out again. Did you have a question, Ebenezer?
Yes.
Yeah.
So the n minus 1, it means we are considering 20,000 samples. So we have to subtract 1. Probably be like 10,000 as well.
Yes. Okay, you asked for it. Okay, so we have a sample size. If you have a population and you're quantifying the variability for a population, you are basically assuming that this is a perfectly normal distribution. So now that is not always the case. And if you have a sample, you will need that standard deviation that you're calculating from your sample versus the standard deviation you have from your population. That standard deviation is an approximation of the standard deviation you actually have in the population. So this would be a t-distribution that you're essentially forming that resembles, and we'll talk about t-distribution in more detail, but I want to go into this. So you basically, what you're seeing in a sample, the standard deviation is less than it is in the population, because in the population you have everything under the moon, right? So there's much more outliers, so there's much more spread, whereas in a sample, you're more likely to sample somewhere from the center because it's just more frequently represented, right? So you have a smaller distribution. You have less variability than you actually really would see from the population. So now you're trying to estimate, you're trying to have an estimate of the standard deviation that the population actually has, and you're doing that by manipulating your distribution a little bit, and you're manipulating it in a way that it gets wider. And it's dependent on the so-called degrees of freedom, how you use them then for inferential statistics or for t-testing. Therefore, you're manipulating your standard deviation estimate from the sample by not using the actual sample size, but using the degrees of freedom to smaller, to lessen the denominator. So you have, so you basically, you have the same deviations as you would have in the population, but you basically make it a smaller denominator, and thereby you're increasing the assumed variability. And you you're decreasing this denominator by not dividing it by the sample size, but using the degrees of freedom. And the degrees of freedom, per definition, is to drop one entry. That is a redundancy in your estimation of the sum of squares. When you think about this, you have the sum of squares and you have your entire sample. You can, in the knowledge of the sum of squares, if you observe that variability and you know that sum of squares empirically, you can drop one observation of your data set, which you can calculate just by knowing all 19,999 entries. So that one is considered a redundancy. And this became a mathematical rule to drop that one. Assume this as the degrees of freedom for the estimation of the standard of the sum of squares to basically manipulate and increase that spread, that assumed estimated spread. Does that make sense? It's a little bit complicated, I know, I'm aware, but it is a way to basically manipulate your estimation of the standard deviation to make it hypothetically more closer resembling the distribution of your population. That's why you're doing it. All right? Okay. Any questions on Zoom? Okay. So deviations from the mean, X-man, and that's one of the issues. It's not shown in a way that I actually would like to see it. Okay, but all of these do have different variations. The problem is the standard deviation per se doesn't really give you an idea how the data distributes, right? So the standard deviation is really just a marker of variability and the standardized variability. The problem that occurs, for example, if you have systemic trends in your data and you have like a decreasing trend of your data with an increase in magnitude. So if you have a time series analysis, you want to see the standard deviation of a particular value. The problem is if you have variability around the mean, that will always result in the same standard deviation. And if you have a systematic decrease, that will also result in an increase in the standard deviation. And you couldn't distinguish between these two dynamics. So the standard deviation really just quantifies the variability, but it doesn't really give you much information about the actual shape of the distribution.
Just in general, standard deviation, what is the main, just I just want to understand the main importance of standard deviation.
The standard deviation is a marker. It is a marker of variability. It becomes important when you want to understand. You can, if you assume a perfect normal distribution, you can, and we get to standardization. So if you read a research paper and you have a mean and a standard deviation given, and you assume that variable is perfectly normally distributed, which you should. If you look at it agnostically, it should be under the assumption this is normal distributed parameter or variable. You can assume under the assumption it's a normal distribution that if you add one standard deviation to your mean and you subtract one standard deviation from your mean, and you have then plus one standard deviation and minus one standard deviation, within the boundaries of two standard deviation, you have 68% of your data. If you take plus 2 and minus 2 standard deviation from your mean, and you have 4 in total, you have 95% of all your data, 95.7. If you take 3 and you go 6 apart, so you have plus 3 and minus 3, you have 99% of your data within these boundaries. So this is why it's useful, because it is a continuation of the principle of statistical testing in a normal distribution, in a parametric test. So if you have this knowledge, this is extremely powerful, because then you know how wide is the data spreading. It's like this researcher from, I don't know, from Germany, UK, or wherever reports this mean and the standard deviation. I really want to understand now, how did their data look like? So they have a mean and they have a standard deviation. You can make this assumption. So you kind of have a feeling how this data distributed. And this is where it comes back, why I think it's important for you in biotechnology management to do this class, because these are the simple basic principles that are super important when it comes to looking at data and like making sense out of what you're reading. So this being said, but this is where standard deviation is important because it builds the segue into the interpretation of the data that you're being presented with. In addition to that, it's the most common way of reporting data. So again, if you have normal distribution, you would always present this as mean plus minus standard deviation. That's like the most common way to report data. If you have data that is not perfectly normally distributed, you would report it as a median and the 25th, 75th percentile. And we will get to that. But yeah, so it's a good point though. Good point though. Like why were we looking at this? But that's really that's no. But you're trying to look at it and you're trying to make sense out of it, and it gives you a reflection of where's the bulk of the data. So a good question. Thank you.
So standard deviation can give us a picture of how the values are close to the true value.
Correct. It gives you an idea where's the bulk of the data. So you have +1 and -1. So that's actually the so-called set score. Within +1 and -1, you have 68%. 2 standard deviation, you have 95.7. 3, you have 99%. It's called the empirical rule. The empirical rule of data distribution. So, but super important, really. It's you will see, if you keep this in mind and you look at the descriptive statistics at the table 1 in a paper, you will look at it with a different eye. If you keep that in mind. And you will, particularly if you have 2 papers now, you have 1 paper from the UK and 1 paper from, I don't know, from Argentina. So you're comparing these 2 papers and you look at blood pressure and you see the mean. Hey, the mean is somewhat the same, but then you compare the standard deviation and you follow that rule and you think about the spread is just much wider. So for these comparisons, these are just super important markers. That is hard to say. This is very hard to say because in the end of the day, and we're going to speak about the central limit theorem soon, the standard deviation allows you to estimate the variability. And what we will be doing so the whole principle of hypothesis testing bases on the principle that you are sampling, and we'll get to sampling and sampling variability next time, you're sampling from a population. So that sample, those 20,000 people that I have at hand, I'm sampling these under the assumption that there is that the mean of that sample is an accurate representation of that mean in the population. Can I make this assumption? No, absolutely not. Because it's dependent on my sample size, because if I draw 20,000 individuals, it's going to be more likely somewhere close to the mean if I just do 15. So a sample 15 is like they could come from anywhere in the distribution, that mean could mean nothing. So then I go from the standard deviation in my sample and the sample size of my sample, and I estimate the standard error of the mean. And the standard error of the mean is basically a continuation of the standard deviation, which is called the central limit theorem. So now you get me started. So now I'm moving forward like 2 lectures. So the standard error of the mean is basically, so you think of a small sample. If you sample a small sample and you sample, let's say, you sample 100 different samples, all of the size of 50 people. You get 50 different means for each of these samples. So these means will have a variability per se. And that variability of these means, that's the standard error of the mean. And with that calculation of the standard error of the mean, which incorporates the standard deviation and the sample size, I am getting to an estimate of how much will this mean vary. These mean estimates vary from 100 samples. So the larger the sample, the less variability, because it's more likely to really reflect that mean of the population. The less standard deviation, the less standard deviation I would expect from the population, the less variability of my mean estimates, my 100 mean estimates.
So that's better.
I hate to say it, but it's.
I mean, if you have a small standard deviation, like number, like value, yes, you will have more of this size. Less probability to have variety, right?
Okay, so if you're going this direction, then yes, then I agree with you. If you just if you use it to report a distribution in the population, you can't really say better because it's a random observation from your population. You're just trying to find out what your population looks like. If you were to look into the treatment effect on, okay, so I have 100 individuals, 50 of these are going to be my control group. They do nothing, and we're waiting for a year. The other 50, I give a blood pressure medication, and I observe them for a year. And then I compare these two groups, and I compare the treatment effect, and I see how effective was actually the blood pressure decrease over the period of 1 year. In that treatment effect, you want to have little variability. You want to see a clear-cut difference between both groups with little uncertainty, a little variability. Then you're right. But if it comes to observing a population, it's likely easier if the standard deviation is small, but it's a reflection of the population. You can't really affect it. So hypothetically, if you have a small, let me just spin this out. If you sample from a population and you have little variability, this is either a sign of you having little variability in the population, which is unlikely because the population will have the universal variability, or you have a terrible sample.
Terrible sample?
Yeah. Because when it comes to sampling, you actually want something that is really reflecting the population. So you want to, if you do a survey and you say like, how happy are you? You want to basically, you want to sample from the population in New York. You want an accurate reflection and not, I don't know, next to a psychiatrist's office where everybody has an antidepressant, but they come out. So it's like, you see where I'm going, right? It's like, so you don't want the sample that is changed in any way. Or when it comes to, I don't know, yeah, you want a representative sample. I'm really not good in examples, so my examples are always terrible. But you get the idea. You really, if you need that variability, you want to see that variability. So you can't, for this purpose of descriptive statistics, you can't really say less variability is good. You want an accurate reflection of your variability. So excellent question. I love that. Okay, good. All right. So squared deviations we talked about, standard deviation not robust. Yeah, well, not robust to outliers. So you got a point there, but it is a convenient tool and accurate tool of describing your distribution. Standard deviation has the same units as, yeah, that's always important. That's always important. A mean, a median, an IQR, a standard deviation has a unit. So if you have weight and you have a mean weight of 78 kilo in the class, in the school, in the university, in the city of New York, that has kilograms. If you have a standard deviation, you have kilograms. If you have a variance, well, that's $1 million question. What is variance? That was the squared, right? So it's kilogram squared. So you preserve the unit. The unit is basically following the same mathematic operation. Standard deviation, yeah. So a standard deviation of 0, you will basically not see ever. Standard deviation always needs to be greater than 0. It's never negative because you squared it and you square rooted it. It's not resistant. The problem is skewness will not be reflected. if you have skewness in your data, your standard deviation assumes it's a normal distribution. That means your data is skewed to the left. Your standard deviation will be large, but you won't know that there's a skewness to the left. Where you will see that skewness, again, if you look at mean and median at the same time, because the mean moves with the outliers. The median stays put. For the variability markers, this 25th and 75th percentile is quite a good marker to see where that skewness is pointing at. So if 25th, 75th is kind of pointing upwards and the 75th is greater, then you kind of know there's outliers or there's a skewness in some direction. Yep.
The 25th to 75th, that is 2 minus 2 to plus 2.
No, that's no, this is 25%. This is this guy, right? This one. So that's 25th of your population, 25th here, 25th greater than the median. So this is really the amount of data that is captured. The +1, -1, +2, -2, that's just an estimate. That is an estimate of in a perfectly normal distribution. The Q1, Q3, that gives you an accurate estimate of where the data, how the data distributes. The other one is just an empirical rule. Okay, alternative measures of spread, talked about this. Yeah, these are, interquartile range, we talked about range, we talked about median absolute deviation, yes, rather rarity, vocabulary, yes, summary, we talked about. What is important is sigma, population parameter mu equals mean or X bar in the sample statistic. Standard deviation in the population is sigma, whereas it's S or SD in the sample statistic. Good. Talk about all of this. Good. Okay. So that was just the theory, and now we're going to go into practice. Now we're going to do this in R. So we have, okay, we have solid 50 minutes. You want to take a break, or you want to? Please.
Error bars.
Yep. 95% confidence interval. Stepping ahead a little bit, this is basically, we talked about the standard error of the mean. Okay, so the standard error of the mean is calculated as the standard deviation divided by the square root of the sample size. So it's this association between the standard deviation of the assumed standard deviation from your sample divided by the square root of the sample size gets you an estimate of how the means of these repeated samples. Let's assume you draw 100 samples, you have this distribution of these sample means. That's the standard error of the mean. If you multiply this with 1.96, and this is where we're coming to 1.96, and 1.96 for a particular reason, and that's probability distribution, which we're going to talk next week about. But 1.96, this is where you're translating. This is where you're translating your population distribution into probabilities. So it, no, don't want that. Set score. Table. There we go. Okay, this is where we're translating the distribution. So we talked about empirical rule, right? We talked about -1 and +1 translating into percentiles. So the set score is basically a standardization approach where you depict the distance of an individual data point from the mean expressed as the number of standard deviation it's located away from the mean. So -1 is center, mean, -1 standard deviation. -2 set score would be 2 standard deviations away. +1 is 1 above the mean, 2 is above the mean. So we're really talking about this only next time. But if you go here to -1, so the way this is presenting is, so you have here the first decimal and the absolute number. You have here on the rows, and you have on the columns, you have the second decimal. So the way you need to look at this is like -1.6, for example, is here, -1.6. Okay, so -1 to prove that I told you the right thing. If you have one standard deviation away, you have the mean is 50%, because it splits it in two equal parts in a perfectly normal distribution. -1, and these are the percentiles. So this is 15.87%. That means at -1, 15.87% are less than that value of -1. So if you have a blood pressure of, okay, let's do weight, 78 kilograms of weight, average weight of every student at Yeshiva University. You have a standard deviation of 14 kilograms. 78 minus 14 is 64. 64 would be exactly that value. That means that 15.87% of all the students weigh less than 64 kilograms. So now 15.87, if you calculate 50 minus 15.87, that's 34.13%. If this is from 0, which is the mean, to -1 standard deviation. If you take now, so this is 34.13. So now +1 standard deviation is again 13 point, because it's symmetric, it's 34.13 again. 34.13 multiplied by 2 is 68.26. So that's the 68% of the empirical rule. And this is packed here in this Z-score table. So this is the standardization of a normal distribution. Yeah. So that's how you would approach this. And when you have now the standard error of the mean, you're translating, because the standard error of the mean, this distribution of means of your 100 samples, also follow basically a normal distribution. It's narrow, but that's irrelevant for now. So you have a normal distribution again. And now you want to know the probability of a particular value that you have from your sample to be consistent with the mean of your population. If you calculate now a mean of your sample and the standard error of the mean, and you're multiplying that with 1.96, which is here, you're at 2.5%. And that translates at this point in a probability where basically you have a sample and you have an assumed distribution around that mean, assuming that you have to the left 2.5%, yeah, and to the right 2.5%. And if your two boundaries of minus 1.96 and plus 1.96 do not comprise the population mean, you have a significantly different sample mean from your population mean. So that's basically how you build a confidence interval. So that's the error bar, because it quantifies the margin of error of your sample compared to the population and to the true mean. So it gives you this bar of the margin of error. Okay, that was a long, okay. It's hard to, so with illustrations, it's easier, so we're getting there. But that's basically, so the error bar depicts the margin of error, and thereby it's that 95% probability that your sample will basically comprise the population mean. Yep. All right, any other questions? All right. Good, so then let's open R, please. We have now a quick practice lab to do. It's basically, it's considerably simple. We have today data from the BRFSS study. It's a telephone survey that did 350,000 people in the US, imagine that. Imagine the time, imagine the money that went into this, and how amazing this data is going to be. So we can open this data file by basically first just cleaning the environment. So that's line number 2 in your code. So if you open practice lab number 2, you have line number 2 is rm list equals ls. That is nothing else but wiping the entire environment clean. It's empty then. So all you did for practice lab 1 is going to become done. And you don't need it because you have the code, right? Then we have here a library that we're loading. So R has a lot of internal packages and has a lot of internal functions, but it will also require the loading of packages that you will get from the source CRIN, from the grant. You download that directly from the R servers. And one of them is Plotrix. Plotrix is quite a useful package, but you don't have it installed on your computer yet. So therefore, you need to go, before you run line 5, you need to go on packages. You go on install. And there you select Plotrix. And you're installing it. So it will, here in my case, it asked me to restart, but that's fine. So you're just installing the package. It will automatically install it. It will do a couple of operations. So you go on packages and install, and you find Plotrix. So it basically will automatically install it for you. And then you can run line 5. And this will now start the library Plotrix. I will tell you later when we get to this, what it actually does, the Plotrix package. Okay, line number 8, and we know already the source commands. The source basically connects with the Open Intro server, downloads the CDC dataset. So now at the end of this line, you have that 20,000 people sample in your environment. So you have 9 variables and 20,000 observations. If you want to inspect it, you can, and this is thanks to the compiler RStudio. You could just easily either you click here on that left button, then it just opens up and it shows you the different variables contained. So that's the left, that's a little pull down menu. Or you click on here on the right, you have this spreadsheet symbol. And then you open this up like an Excel spreadsheet. So you can scroll through it, you can look at the individuals that are in here. So you have here a couple of parameters. You have your gender, you have age, you have desired weight and actual weight. You have, I didn't even know that was in there. Then you have height. Then you have smoking status. You have health plan. That one I forgot. Oh yeah, any exercise, whether the individual exercises or not. And you have the general perception of health. Does that individual, the respondent, consider himself to be considerably healthy? So now the questions in the practice lab, and this is really where the basic starts, but this is so important to understand that data, understand what data variables this contains. You can do this with ls. ls and parentheses just gives you everything in the environment. So it tells you in my environment, I only have the CDC object. If I'm digging deeper now in line 15 and I say ls CDC, it will give me a list of everything that is contained in my object CDC. So I'm being more specific because ls empty just gives me generally everything that's floating around in the environment. I do ls CDC, it basically gives me everything that is inside of my CDC object. Why do I show you that? Because so now we're getting a little closer to actually kind of get a solid handle on how to approach these objects. So we have here 16, line 16. We have the variable A, or object A, and we have here an equal. So this is the R equal sign. You can hypothetically, you can make it an equal sign, but it's just traditional in R, you use the smaller sign and the hyphen to assign whatever you want to assign to an object. So when I say equal sign, that's what I mean. So A equals 1 creates now the object A and assigns the value wanted. Simple, right? If I say A equals C, you will remember the concatenate, right? C is concatenate. 1, 2, 3, 4, 5. It basically creates now, oops, that was not good. Creates now a so-called vector. So first it was just an object that contained one numerical value. Now it's an object that contains a vector, a numerical vector. And you will be exposed to all of that on data camp. So you will know what that is. So this numerical vector essentially can be any list of numbers. It can be 1, 2, 3, 4, 5, or it can be CDCH. So CDCH is CDC object. So this is what we just loaded. $sign over there. $sign indicates I want something from that object, and I want the variable age, which I know is part of my object. So I know it's in there. So if I say CDC $age, it will query the entire age variable. And with the equal sign, I just can assign it to age. So now basically, if I run line 18, my A basically contains 20,000 entries for the age of my CDC sample. So why am I doing this exercise? Not to bore you, but to show you that you can assign whatever you want to assign to that object. I will just take it in and assign that to the object. And this is important conceptually because you can now specifically address whatever position in that object you want to address by using the bracket. So A bracket 3 will give you the third entry in your vector. So that individual was 49 years old. So you can do this with A3, you can do this with, and if you compare it here with line 20, same entry. So it's consistent, it's just pushed it over, right? Yep.
So line 18, A is H column in the CDC data.
It's not a column at this point. Okay, column, good point. So H is a column. CDC is a data frame like the Excel spreadsheet. But now what R does now, when I assign CDC $H, when I take this, this column, I rip it out and I'm assigning it to the object and I make it a vector. So conceptually, I would rather look at spreadsheet column vertically. If I rip it out and I put it in and make it a vector, then it's like horizontally. In my head, it's just.
Because when I run this, it's not showing any data.
Okay.
Oh, it's
You need to run it first, yeah. Yeah, CDC, it's over there.
Yes.
Yeah, so if you do A bracket 3, no, A bracket 3, you need to go in your script. A bracket 3, line 19, will give you 49. That's the third entry. And CDC H brackets 3 gives you the same entry.
90.
That's the age of the third participant. So it just gives you the third spot in your in your variable. If you're going now into CDC, and this is important, and this is just conceptually again important to know. If we do CDC bracket 3, 8, you have the comma separates row from column. So I know that if I do call names, CDC, that's the column names. I know that age is the 8th entry. So it's 1, 2, 3, 4, 5, 6, 7, 8. So it's the 8th variable as a column. So if I do 3, 8, that gives me the 3rd row in the 8th column. And that is, you guessed it, 49. So that's how what this basically all comes together, right? So you can address various things, but you just got to know how to orient yourself. And this is why I'm doing this exercise. It's basic exercise to basically show you how to orient yourself in R. Okay, good. Another very important command when it comes to the investigation of your data set is str. Str basically gives you an idea what is each variable in my object. So if I have now a characterization of these variables, I see here numerically, I see here integers, and I see factors. So numerically is quite logically, but if I look here at this, it's basically it's binary. So it's a categorical variable that just was recognized by R as a numerical variable. I can leave it like that for now, but I can also transform it in a factor. But for now, I wouldn't do that. We'll learn how to do that quite soon. What the charm of a factor is basically a way how R recognizes this as a categorical variable. So it gives you the number of levels. So it recognizes male and female, but it basically codes them, or it has stored them in ones and twos. And this is one thing that I very much dislike, and I know where this is coming from. That's a typical SAS behavior. So SAS programmers, SAS automatically assumes that you will code biological sex into ones and twos. It's beyond me why they do that. I would not do that. What I would do if I were asked, yeah, we'll talk about that later. Okay, so ones and twos indicate males and females. You just have labels on it. Why that is great is if you have something in a factor, if you go in summary, CDC, gender, you're basically getting automatically a breakdown males and females. So you have 9,569 males and you have 10,431 females. So that's str is a very useful command to basically understand your data set in more detail. If you use unique, you basically get you get each unique entry. So you know now, based on unique CDC general health, you know that there are 1, 2, 3, 4, 5 different entries, 5 different unique values that can be in your data set. You know from str that this is basically 5 levels of factors. So if you do now summary, CDC, general health, this basically gives you 5 different categories and gives you the count for each of these categories. That's why factor is actually a very powerful tool. To recode your categorical variables and factors gives you a lot of flexibility in R to basically summarize them. Okay, but next. Okay, so this is kind of, how you can start your investigation. So you kind of describe the object, how many parameters, how many cases, how many males, females, we did that. How many older than 25, how many older than 35? So this would continue here. So we have summary, CDC gender, we just did that. And now you want to do something different. Okay, so we have determined that gender is coded into males and females, M and F. right? So I don't like this way of depicting this data. I'd rather have this as 1 and 0, where 1 is basically females and 1 is females and 0 is males. So I'm recoding this in a new variable. I'm recoding this into female, yes, no. Becomes a binary variable. Is this a female participant or is this a male participant? If she is female, I assign a 1. If she is not female, I assign a 0. So CDC female, if else, is basically just like in Excel, an if formula. So you do nothing else, but you assign a certain value to your new variable if a certain criterion is met. So I create a new variable, which is CDC female. I assign to that with my if else a 1. So so you have 3 different parts of that. You have if else, this is the criterion. So if CDC gender double equal sign, so equals F, then assign a 1, otherwise assign a 0. Make sense? So you have 1 criterion. So basically you have a new variable. Let's create the variable first. Okay, just to illustrate that, I create the variable. So now we have 10 variables. I've created now an additional variable, which is here all NA. NA is the way how R expresses missing values. So I just say like, open this variable, fill it up with missing values, fill it up with NAs, and then we'll talk what we're going to do with this. So what you want to create now is an additional variable where this individual would be a 0 because he's not female. This F would become a 1 because she is female. So you want to create a new variable that basically derives from the respective variable gender that is coded in a way we don't like into either 1s or 0s. So it's yeah. So this command here that I wrote here, the CDC $ female equals NA, created a new variable. This new variable is all NA. So these are all missing values, all NAs. And now I want to fill these NAs now with information from the variable gender. So I want to make this a variable female, yes, no. If it's yes, I give it a 1. If it's no, I give it a 0. So now I am finding all my Fs and I fill them with 1. F and all my Ms and I give them a 0. So, and I do that with the function if else, where I say if else CDC gender equals F, then I give it a 1, otherwise I give it a 0. Yeah? Make sense?
Professor, how do we create the
NA? The NA was here. Yeah. I can add this here. So it's basically CDC female equals NA. Well, now it's 34. Actually, I'd rather not have it in there, so it's down here. CDC female equals NA. That creates a new variable, but you don't need this variable. I just did it for the demonstration purpose. You don't need to do it. Yeah, you can just jump into line 34 and just run line 34. We'll create the same variable. So, but again, the idea is to create a female variable that basically has a 1 for all females and a 0 for all males. Good. So we're doing this now. We're filling this up. And now we go back to our CDC data set. And here we have filled it up. Makes sense, right? So this is if else. And now, why did I do that? Because one way to count all the females is by basically doing summary CDC gender, like we did up here. So that was line, what was it? Line 33. That's one way to do that. Another way to do that is to sum all the entries for females. That gives you 10,431 females. So it's the same kind of approach. You can alternatively do now where you could also arithmetically derive now the number of males, which would basically be length, which gives you a count of all entries, minus the sum. So that gives you the number of males, right? So you can use all derived numbers to do arithmetic operations with it. So these two numbers are the same as these two factors, or these two levels of the factor. Another way to do that is you can use the if else, where you have CDC gender, and this is the exclamation mark equal sign that's unequal to. So where you say, okay, so my entry is unequal to M. And once it's unequal, you assign a 1 again to wherever that criterion is met. So that unequal M equals F, right? And if it equals M, then it's 0. So same principle.
So the unequal sign is the exclamation mark.
What was the question? Sorry. The unequal sign is exclamation mark equal sign right next to it. Yep. So these two are basically then allowing to do that. Okay. So now the next question, and now we're coming back to length. You remember length? If we do length CDC, we're getting the length vertically. So we see now that CDC has 10 variables, which we know from the environment, right? If we do length vertically, we would do length CDC, let's say height on a female. So that gives us 20,000. So that's the count vertically, right? So if you do length CDC, you only go horizontally. If you do length vertically, you get horizontally, you get vertically all entries. If you have length CDC female, and now it's getting a little tricky. So we want all entries that are greater than 25. So that we would do by restricting our vector with the brackets. So remember how we did vector bracket 3, and we got the third entry. You can also utilize this to basically employ a criterion of all the entries of the vector that you want to select. So if I use this here in the fashion like a line 40, CDC female, CDC age greater than 25 is basically only selecting the entries that are greater than 25, right? You're just employing the same logical criterion to your vector. So I have this vector of 20,000 individuals, and I'm cross-referencing it with age, and I say only count those that are greater than 25. So if I run the same, the entire code here for line 40, I get 17,272 that are greater than 25. If I run line 41, I get 13,000. So there are less individuals older than 35 than there are less, now there are less individuals older than 35 as compared to all that are older than 25. So and the difference between that and that So if I would want to do an arithmetic calculation of this and this, I could just bring this in the same line and I could calculate the difference. That's the difference between those two. So I know now that 4,056 individuals are between 25 and 35 years old. Make sense? Yes.
This is for female greater than 25. Is length?
No, length female. So that's a little bit misleading. Length female is just counting the entire vector, irrespective of what's in there. So it's counting just 20,000. Yeah, you forgot the lengths. You got to do lengths.
I should do the length.
Lengths too, yeah.
Something like this.
Yeah.
So I want to start my.
You didn't run this up there then. Run this first. Now run it again. Now run. Just go through. Go. See? You always need to run every line. So just because you have the line in your code doesn't mean that R already has done the work. So you need to run every line all the time. Not multiple times, but each line. Each line needs to be run. So it's always, we're creating a standalone code that need to be run as a whole. So in the end of the day, you want to do Control A and run the whole thing down and not touch it ever again. And we will do it. That's part. We will export PDFs. We did export PDFs. We will create new data files. We will create tables, and all of this can be done quite simply. And that's the beauty of our basically can do this automatically and then put them in a respective folder in which you want to have it. Okay. So this was this. What else do we want to have? So we want a histogram, a distribution of age as a histogram. We know already how to do that. So this is the histogram. Then we have summary. Summary is a very powerful command, and we looked at this already last time. So you basically get a min and a max, which is the range, right? Then we have first quartile and third quartile. That's our IQR. And then we have mean and median. And summary is nice in that regard because mean and median depicted at the same time will at the very same time show you the skewness of the data, because if the mean is pulled towards the outlier, you basically know already in which direction that skewness goes. Although we see here that this data that's a solid normal distribution. So you can actually, if we look at this a bit more in detail, and we increasing the granularity of your histogram can be done with breaks. Breaks equals 20 should do the job. Yeah, basically shows you a much nicer distribution, right? So if you increase the breaks, you get more breaks, which indicates the size and the boundaries of the bins. Okay. Now, height, weight, we can do the same with weight. We get now with ST. ST is the R command for standard deviation. So we have here standard deviation. And we have a standard deviation here also for weight. So that's with ST. Now we want to know what's going on with outliers. So we see now the distribution of weight. So we have maximal entry of 500. I'm not sure this is pounds or this is kilograms. I think it's pounds, but it's still massive enough. So we have, we want to investigate our outliers now. And this can be done by looking at the data set and restricting it only to those entries where weight is greater than 400. So this basically is line 52. So now there are basically 3 individuals that have a weight greater than 400, which are these 3 people, 2 males, 1 female. 405, 495, and 500. In poor health for both of them and fair health for one of them. One of them is even a smoker. So, and smoker was 500 pounds. That's some health behavior. Okay, so we have, then we want to see the distribution of age. So we did the age calculation. Now we do a histogram of age. We have here a little bit of a skewness. I wouldn't pay too much attention to it, but you get a bulk of respondents somewhere in the age of, I would say like 25 to like 55. So that's the age distribution. Here you see to histogram, you see also some additional labeling. So you can do with XLab, you can basically label the x-axis. And you can, with main, you can give it a main title. And then basically we can continue to calculate summary statistics. Mean is basically calculated with the mean function, although we know already from the summary what the mean is. We have median, with summary. We can now pack it again into an object. We can calculate here with A3, you're basically calculating the median. So A here becomes the summary. So we're assigning in line 66, we're assigning summary as a function into A. With A3, A3 is actually not good. Why did I do that? We actually want to do this. Please change on line 67, A3 to A2 and A4 to A5. Sorry for that. Because that becomes now, so we're extracting now with A2 and A4, we're extracting first and third quartile. And we can now calculate by hand. So this is line 69. We can calculate now, we need to change this to 5 and 2. We can calculate now the interquartile range as 26. We can also quantify the variance with the VAR function. The square root of variance basically will give us the standard deviation, right? We know that, or the SD function gives us the same. If we are dividing now, and now we're coming to the standard error of the mean, and this is why we needed the Plotrix package, because the Plotrix package contains a standard error function. So SD of our age divided by the square root of the length, so that's the sample size, will get us to a standard error of the mean. So remember what that means. So we have age. Age has, what was the mean? I forgot the mean. We have a mean age of 45. And we have a standard deviation of 17 around that 45. So we know that 68% of our respondents were between 45 minus 17 is 28 and 62. So that's 68%. And if we were to look at 100 samples, and we sample 100 samples of our 350,000 respondents of the same size, and we would look into the variability of these mean estimates from our samples, from our repeated samples, we would get a variability of our mean of 0.12 years. So that means that the sample of 20,000 results in very little variability of our mean estimates. So that's the standard error of the mean. With the Plotrix package, you can also calculate it with the standard error function. This is here line 74, gives us the same standard error of the mean. This is the IQR. So now for the calculation of the mode, and I was hesitant to actually add this to the code because the mode is, I think it's rarely ever used for calculation. It's rare that somebody ever even quantifies it. In case you are ever to use that, You have on line 77 and 80. I have built you a little function, so that's a manual function that will basically determine the highest entry in your density plot. So that basically is a function. If you run 77 to 78, it will create here a function on the right, which is called getMode. So if you want to use the getMode for the age variable, you write getMode CDC age will basically getMode. Yeah. GetMode will basically get you the mode of 40, which if we look here at the age distribution, that's the highest peak. So that's just a little function that basically determines the highest, the peak of the normal distribution. Then lastly, here's a little bit of an overview of how to quantify your data in a frequency table. And you can do this quite simply with the table function. So that's basically a table of general health, so general health perception and gender. So the way you want to design these contingency tables is basically by quantifying them in this fashion. So you basically have male and female. You have the 5 different levels of the general health perception variable, and you get the respective counts for each of these groups. So now if you were to pack this into a bar plot, you can simply do this here with that little function bar plot that basically will allow you to summarize it in a bar plot, which is kind of nice to do. And basically gets you this plot. And that's for you to compare how is the health perception. Is it more frequent in males versus females, that they're feeling good about their health or they have poor health? So that's one way to analyze this data. It's a useful function to have. Okay. Then we have for practice lab, and that's pretty much all we needed to do. Well, there's one additional entry that we didn't show the data should be. Okay. Okay, any questions to that? So far, so good? Yeah, so please submit it in the same fashion as last week. So please rerun the entire code. First, click on the console, press Control and L. Click on the script, press Command and A. Run the whole thing down. And then copy paste it. If the plots, please export and add to the submission. Okay. All right. And copy this into text edit. Copy this into text edit, create a new document, copy it in there, and save this as BTM6000, family name, practice lab 2. Yeah, so I really encourage you to go line by line and try to reproduce all of these, because these exercises, they're kind of consistent with what you are asked to do in data camp. It's just nicer to kind of have the data camp exercise and redo them with a real data set. And the BRFSS study is actually kind of interesting. It kind of may already be somewhat hypothesis generating for your final project. So some of the data you will have in some shape or form also in the enhanced data set. All right, any questions?
For this one, we have to create output product, or
excuse me?
Product. We are going to do the same output product, or
the same output. Yeah, please create that output, copy it in a text file, like I just showed. I just rewatched the video. Like I've just done it, and save it with BTM6000. 6000, not 600. And no. Okay, it's supposed to be 6,000. And your family name and practice lab too. Okay.
Professor, one more question about
Yes.
the graphs and the plots. You want us to export each one of them that the code created, or just the final one?
No, export the plots, please. You can either do it by hand or you can do it automatically. So you can use the PDF function. You can also do it by hand here, but basically save them as PDFs.
Okay, but my question is, like, there were several different histograms also that were generated. You want those as well, right?
Yes, and you can go back on them.
Oh, great.
So
Okay.
here with the arrow, you can basically go through all the plots that we have created over the course of running that session.
Okay, cool. Thank you.
Yeah, sure. All right. Any other questions from Zoom? If not, I think we can conclude for today. Wish you a good rest of your week. And next week, it's going to be a virtual session. We're going to meet at our regular time, but on Zoom.